Okay. Hello. Um, Today we're going to go over the midterm one review session. So, some people requested to go over the acid-base strengths of free radical halogenation and also the transition states. So, what would you guys like to go over first? Acids and bases, or free radical halogenation and the transition states? So let's go over halogenation. Okay, so for free radical halogenation, here's the general equation for it, where we have some kind of hydrocarbon, RH, reacting with some kind of X2, where X could be fluorine, chlorine, or bromine. It will not be iodine because iodine is not as reactive. And when we react this with light or heat, we are going to substitute this hydrogen here with a halogen, so either fluorine, chlorine, or bromine, and a strong acid HX, right? Where this H will come from the H of the haloalkane here, of the halogen right here, and then this X here will come from one of the X's of the X2 right here, right? Where there are three steps of the mechanism here. There's initiation, propagation, and termination. Initiation, which for initiation, we're gonna initiate the radical chain and come from 0 radicals to 2 radicals, right? So here's the mechanism for the initiation step. Let's say we have this X bonded to that X right there, and we shine some kind of light or heat energy into it. This bond here represents 2 electrons, where to show the movement of 1 electron, we have to draw a single hook arrow like that. So 1 electron is going to go to that halogen. The other electron is going to go to that halogen right there, right? And this would create 2 X radicals like that, right? So that's initiation, coming from 0 radicals to 2 radicals. For propagation, we're going to propagate the chain. So we're going to exchange radicals. We're going to start with 1 radical and end up with another radical. And there are 2 substeps of propagation, propagation step A and propagation step B, right? So let's look at propagation step A, where we're going to use this X radical that we just formed in the initiation step and the hydrocarbon right here, right? Where we're going to form the HX by bonding the hydrogen with the X there and giving this R hydrocarbon chain a radical. So when we do that, we are going to get this set of products, R radical plus HX. Right? Does this make sense so far? Any questions on this? Right. So that's the first substep of the propagation. We do not have our haloalkane yet, right? The second substep of propagation is that we're going to bring in that R radical that we just formed and another equivalent of X2, right? This R radical here is going to make a bond with that X, and then the other X is going to get the radical. So that's going to be Rx plus X radical right there. The reason why I did not use another X radical to create this haloalkane is because if I used an X radical, right, that's going to create this Rx, but with no other radicals. That's termination, not propagation. So in the midterm, if they ask you to draw out the mechanism or a reaction of a propagation step, make sure you start with 1 radical and you end with another radical. If they ask for termination, then you could use the X radical to form the Rx with this R radical here, right? So these are the two substeps of propagation. Termination, there's a whole bunch of reactions that you could do where you're going to terminate the radical chain by starting with 2 radicals and ending with 0 radicals, terminating the radical chain. So an example would be X radical combining with another X radical, R radical binding with another X radical. It could even be an R radical bonding with another R radical here. And this gives undesired side products. Okay. So 2 X radicals coming together would form your starting material again, X2. 1 R radical and 1 X radical would form your desired product, the halocane RX. And then this is the undesired byproduct here, the bulky hydrocarbon chain RR. Right? Propagation is going to happen 1,000 times more than initiation and termination. Right? So initiation and termination steps are more rare than propagation steps. Propagation steps are more common, right? So that's the whole reaction and mechanism for free radical halogenation. There are more conceptual stuff for this, but does this mechanism make sense so far? Yeah. Okay, that's good. So now let's go over the other concepts of this, which is going to be the selectivity factors, right? So the general selectivity for these is that depending on what halogen you use, they would go for a certain spot at the hydrocarbon chain, right? So let's say substrate, right? If you use fluorine, chlorine, or bromine, fluorine would most likely select for the primary carbon. Chlorine will most likely select for the secondary carbon. And bromine is very selective. It selects for the most substituted carbon, the tertiary carbon. Right? So, for example, if we have this hydrocarbon chain right here, and we react that with Br2 and light, then this Br2 is very selective. It's going to select for the most substituted carbon, which is this tertiary carbon right here. So that would give this product there. Right? So another thing is that since bromine is very selective, then it is going to have a late transition state. Right? It's not going to happen as fast as fluorine. Fluorine is unselective. So it's going to have an early transition state. It's going to happen way faster than bromination. Fluorination also has an early transition state, but it's in the middle. It is in the intermediate between fluorine and bromine. Iodine will have no reaction at all. Right? Let's do some practice problems with this. Let's see. Halogenation right here. Yep. Okay. And also, since this is unselective, this tends to have a low activation energy. And this one that is very selective, late transition state, tends to have a high activation energy. It requires more energy for this reaction to go through, right? And this also tends to be more exothermic. This tends to be less exothermic, right? Because the more exothermic it is, the faster the reaction will be, less selective, low activation energy. Like Gen Chem concepts, right? Okay. Let's see. Okay. So let's do a practice one with this. Write the two propagation mechanisms with cyclopentane and Br2 plus like. Right. Okay, so for this question here, they're asking for us to write the two subsets of propagation. Right? So let's just actually do the whole mechanism. Initiation, right? What would the initiation step look like? Initiation. Okay. What would that look like based on this question here? Yeah, bromine would form two radicals, Br2, where we are going to cleave this bond homolytically, meaning that we give one electron to that one bromine and the other electron to that other bromine, giving us these two bromine radicals. Right. Now for propagation, what is propagation step A? Right. And then you guys can take a picture of this mechanism as well to help with this problem. Initiation, propagation, and termination here. Okay, let's go back. So propagation step A would have a cyclopentane like that. And I'm going to draw out one of its hydrogens to show that carbon-hydrogen bond. Yeah, the bromine radical will react with the cyclopentane bond to H to form a cyclopentane radical in HBr. That's right. This Br radical that we just formed right here is going to make a bond with this hydrogen from this single hook arrow here. But this bond represents two electrons. So we have one more electron on this bond, where that one electron is going to make a radical on that carbon right there, making the cyclopentane radical. Right. Which is that radical right there, plus HBr. This new bond between hydrogen and bromine has two electrons. Those two electrons are from this electron and one of the electrons of that bond right there. Right. What would propagation step B be? Cyclopentane radical reacts with Br2 to form a cyclopentane bonded to bromine and bromine radical. That's right. And what is the reason why we cannot use a bromine radical to react with the cyclopentane radical, right? Why did we have to use another Br2 to form the haloalkane instead of a Br radical? What's the reason? Yeah, for this specific part of the mechanism. Right. So these are the two propagation steps here. Right. Where we started with one radical and we ended with another radical for both cases. One radical, another radical here. The reason why we cannot use another bromine radical to react with this cyclopentane radical is because if we did that, that would not be propagation. That would be termination when we combine two radicals together to make zero radicals. This is termination. If you use the hydrocarbon radical reacting with another halogen radical, they bind together to make their haloalkane with no other radical. So that's not propagation. That's termination, terminating the radical chain. Right. So that's the point. Read the question carefully in the midterm. If they ask for the initiation, that's the simplest question because it's just splitting the bond into two radicals. Propagation is probably the hardest one because there's two substeps. And then termination, there's a whole bunch of termination reactions you can do with all the combinations of the radicals that you can bring together and form. Right. Okay. Any other questions on free radical? Just to clarify, steps A and B always happen, right? Yeah, steps A and B will always happen in propagation, but they happen sequentially. Step A happens first, and then step B happens. Because we need step A to happen to form this R radical, the hydrocarbon radical, for step B. The step B gets its R radical from step A, right? And then step B gets this desired product that we want, which is the hydrocarbon right here, RX, like that. So for step A, they always interact with H. So for step A, they always interact with H, right? The X radical always makes this HX for step A. That's always the case. Is this example cyclopentane radicals form something in termination? Yes. So we could go over all the termination reactions as well, just for extra practice. Do you guys still need this board, or I could erase it and go over the termination reaction? Okay, let me erase this board really quick and then go over the termination reactions. Oh, actually, let me just keep this because I'm gonna give you guys another example, which includes all of the mechanisms for this reaction here and predict the product as well. Right. Okay, so termination. We could have a bromine radical reacting with another bromine radical. We could have the cyclopentane radical reacting with a bromine radical, or we could have two cyclopentane radicals reacting with each other to form the undesired product. Right. So these two radicals can come together and terminate the radical chain. Two radicals together to make zero radicals, that's termination. Right. This would make Br2. This would make the desired product, the haloalkane. This would make this undesired product, byproduct. This bulky hydrocarbon chain right here. So those are the termination reactions, the possible termination reactions for this specific example. Okay. Any questions on this before we move on to another specific example? Okay. So let me give you guys this example. So I want you guys to predict the products here and write out all the mechanism arrows: initiation, propagation, and all the possible termination reactions for this reaction here. Right? So first, we have this hydrocarbon chain, and the reagents we have is Br2 and light. Where would Br2 attach to this hydrocarbon chain here? Right? Which position of this hydrocarbon chain? Right. The bromination is very selective. It's selective for the most substituted carbon, which is going to be this tertiary carbon right here. And this is a tertiary carbon because this carbon here is bonded to 3 other carbons. 1, 2, 3. Right. So the product here is going to be that right there. Right. So let's go do the mechanism again just for extra practice. Initiation. We'll have this homolytic cleavage to form 2 bromine radicals here. Right? For propagation, there are 2 steps, A and B. They always happen together. And like Jesse said, the step A would interact with the hydrogen of the carbon that it interacts with, always forming an HX. So this is the hydrogen right here that's going to get reacted with the Br. And then the other electron is going to make a radical on that tertiary position, like Ryan said earlier, right here, right? And that would form HBr like that, where this bond between H and Br has 2 electrons. Those 2 electrons are coming from this 1 electron from the bromine radical and the other electron from that bond right there between carbon and hydrogen. The other electron is going to go on that tertiary position right there. That's the radical right there. Have you guys learned about radical or carbocation stability and hyperconjugation yet? Yeah. So what that basically is that let's just say we have a CH3 methyl radical, and then a primary radical, and then a secondary radical, and then a tertiary radical. This is going to be very similar to carbocations as well, where we have positive charges on the carbon. Right? Notice how the more substituted the carbocation or radical is, the more stable it is. That's because of hyperconjugation. These R groups here, they are donating electrons inductively, making that positive charge more stable, right? And they are able to donate electrons because there are like sp3 orbitals around. But the most important thing here is think of it as like friends. The more friends the carbocation or the radical has, the more happy it is, the less lonely it is, the more stable it is, right? So that's hyperconjugation. The more substituted it is, the more stable it's going to be. And that's going to go more into like the reactions you learn for SN1, E1 reactions, but that's later on in the summer session, right? So that's why this tertiary position is going to be stable, where for propagation step B, we have that tertiary radical here that's going to react with another Br2. We cannot use another Br radical because that Br radical would terminate the radical chain. That's not propagation. We need to create another radical, which is another bromine radical there, right? But this one here would create our desired product, the haloalkane, bromine plus the Br radical. And I think termination you guys got already, or unless you guys want to go over the possible termination reactions, right? The Br radicals coming together to form Br2, the R radical reacting with the Br radical to form the desired haloalkane, or the undesired product where the two R radicals combine together to form that bulky group. Right. Yeah, I think that's good. Okay. And since this is bromination, this will have a late transition state because it's very selective, high activation energy, and selective. Yeah, selective. Okay. Will fluorine and chlorine do the same since they are less reactive? So if we change this up, right, fluorine will usually go for the primary carbon, and chlorine will usually go for the secondary carbons, right? So that's the difference. They will do the exact same mechanism, but the carbon that they attach to is going to be different. They have different regional selectivity. Regional selectivity meaning that they select for a different region, right? Bromination is the most selective. It selects for the most substituted carbon. Fluorination usually goes for the primary carbon, and then chlorination usually goes for the secondary carbons. Right? So that's the difference. For chlorine, is there a preference to a specific secondary carbon? It depends on the actual structure, right? Because that goes into like the theoretical and experimental ratios with the different things. I'll go show you guys that as well. But I didn't see any question like that on the practice midterm that he gave you guys. So I don't think you guys need to worry about that. So do you guys still want to go over that concept, or move on to the next line? Right? But because it will matter depending on the example. Like the relative abundance, selectivity factor. Have you guys learned about the selectivity factor table where depending on what halogen you use, F2, CO2, Br2, and what kind of substrate is it, primary, secondary, tertiary, there's ratios of products. Like there's a whole table where primary is all 1, and then secondary is like 1.24, 80, and then tertiary is like 1.45, 1700. Have you guys learned about that table? Because Levens did, and Nusiri did, but for Ling, I've never seen him teach 118A before. This is like my first summer session according like seeing him teach this 118A class. So I'm not too sure on how he teaches this free radical halogenation stuff. But did he go over something called the selectivity factor table? Okay, so don't worry about that, right? Because for the question that you asked, Ryan, the chlorine, is there a preference to which secondary carbon? It has to do with that table, right? But in summary, just think of it like fluorination goes like prefers the secondary carbon, fluorination prefers the primary carbon, and bromination prefers the tertiary carbon. Oh, right, the change in enthalpy in those tables. Yeah, that right there is talking about like the exothermic and endothermic of the reactions, where fluorination will have the highest like heat released because it's the most exothermic, and then iodine is going to be the least, or like even positive because it's endothermic, right? Bromination is the least exothermic. It still happens, but it's the least exothermic because it's the most selective. So that's the conceptual thing about those tables, right? Those tables would not be tested like on the midterm. It's more conceptual, like multiple choice question type, right? Like, right? Like it might be like which one's the most reactive, the most selective, which is fluorination, the F2. He could also ask which one is the most selective, right? Like chlorination, bromination, fluorination, and then you choose the bromination one, the most selective one. You can also change it up by saying which one is let's see, which one is the most like endothermic and will not react with any hydrocarbon even in the presence of light and heat, right? Which is I2, iodine. Iodine will not react with a hydrocarbon even in the presence of light and heat. But most likely, for the mechanism arrows, like this is what you need to know for initiation, propagation, and termination. Calculate the percentage of which bond is favored and show that calculation. Which bond is favored? Wait, let me check your notes really quick. Which notes is this from? Which day? Let's see. July 3rd, I think, or July 2nd. Statistic ratio, experimental ratio. July 3rd. Okay. With all the statistic experiment. Oh, right here it is. Bond is favored. Activation energy. Relative reactivity of the hydrogens are secondary hydrogen, primary. Yeah. So I think he just showed that in lecture to back up the summary that he gave at the end of why fluorination is the most reactive, and then chlorination, and then bromination. It's all because of that data that he showed you earlier, right? That's all you need to know. I don't think, I highly doubt that you need to calculate that, because I've never seen a problem where where a professor asks you to calculate that. But yeah, well, I would know just because I've never seen Ling teach, and he didn't include this in his practice exam, so I wouldn't worry about that. I just know the conceptual stuff where fluorination is the most reactive, and then bromination is like the most selective, that selects for the tertiary, most substituted carbon. Yeah. Okay, so what else could be tested for free radical halogenation? Okay. Yeah, this is very similar to what we did earlier. Okay, are you guys ready to move on to acids and bases? Like how to determine which one's the stronger acid and why? Okay, let's do that. Okay. Okay. So to determine which one is the stronger acid, right? You first deprotonate the acids to get the conjugate bases, right? And then from there, the more stable conjugate base will equal the weakest conjugate base, right? Because the more stable something is, the less reactive it is, right? Because the more stable it is, the less reactive the conjugate base is. And the less reactive the conjugate base is, the weaker it's going to be. And in Gen Chem, we said that the weak conjugate base comes from the strongest acid, the strong acid. Right? So the relationship that I like to think about is just the stability of the conjugate base. The more stable it is, the stronger the acid that it came from. And there's an acronym to determine the stability of the conjugate base, which is CARIO. Right? Where C will stand for charge, A will stand for atom size, R will stand for resonance, I will stand for induction, O will stand for orbital or hybridization. Right. So let's think about the charge of the conjugate base, right? What is more stable? A negative charge or a neutral charge molecule? What is more stable? Yeah, neutral is more stable. Than a negatively charged molecule, right? Now let's think about the atom size, right? And let's say that both conjugate bases of the acids that we're trying to compare are both negative charges. Will the negative charge be more stable on a larger atom, more polarizable atom, or would the negative charge be more stable on a smaller atom, a less polarizable atom? So a negative charge on a larger atom is going to be more stable than a negative charge on a smaller atom. And that's because think of it as the negative charges being more able to move around, breathe, and be delocalized, making it more stable, right? It has more space to move around in the larger atom than compared to a smaller atom. And I'll give you guys examples on each factor after this. So let's think about resonance, right? What makes a molecule more stable? A molecule that could do resonance with a negative charge, or a molecule that cannot do resonance and that is localized, right? The one that can do resonance and is delocalized, or the one that cannot do resonance and is localized. Resonance delocalized, right? So delocalization, delocalized is better than localized, right? Delocalized is basically meaning that that molecule can do resonance. Localized means that that molecule cannot do resonance, right? So let's think about induction. There are actually three factors that goes into induction. It's going to be more electronegative atom, increases acidity, right? Because the more electronegative atom will be able to withdraw electrons or the negative charge better, making that negative charge more delocalized, more stable. The other thing is going to be a larger number of electronegative atom. So let's say you have the same electronegative atom like fluorine. In one molecule, it has one fluorine. The other molecule has two fluorines. Those fluorines have the same electronegativity, but the one with two fluorines would be more stable, or like more acidic, because it has more electronegative atoms. So that's the other factor, right? The third factor is going to be the proximity to the negative charge. So let's say that we have one fluorine and the one fluorine molecule next to a carboxylic acid, for example. But in one molecule, the fluorine is like way at the end of the other side of the chain. And then the other molecule, that fluorine is right next to the carboxylic acid. The fluorine that is right next to the carboxylic acid will be able to stabilize that carboxylic acid more because it's way closer, right? And I would argue that the proximity factor is the most important, right? Because even if you have chlorine next to that carboxylic acid, and then you have another molecule that is a fluorine, but that's farther away, the one with the chlorine, even though it's less electronegative, is the one that's going to make it more acidic because it's closer to the carboxylic acid. I'll give you concrete, clear examples after we finish this acronym here, right? Now let's talk about orbital and hybridization. Will a negative charge be more stable with more S character or less S character? Yeah. Well, um, the negative charge would be more stable on more S character. That's right. Because think of it like this. The more S character something has, the closer it is to the nucleus. And we know the nucleus is consisted of protons and neutrons, right? And we want more S character because we want the negative charge to be close as possible to the nucleus because opposite charges attract. This negative charge here is attracted to this positively charged nucleus, so we want more S character, right? So SP will have the highest S character, and then SP2, and then SP3. Specifically, SP will have 50% S character, SP3 will have 33% S character, and then SP3 will have 25% S character. Right? And the way you can think about this is that in the sp orbital, there's one S orbital and one p orbital hybridized, right? There's one S out of the two hybrid orbitals. One out of two is 50%. For sp2, there's one S orbital and two p orbitals, three total. But there's one S out of the three. One out of three is 33% S. For sp3, there's one S orbital, three p orbitals. That's four total. But there's one S out of the four. That's 25% S character. So a negative charge on the sp atom is more stable than a negative charge on sp3 atom because the sp atom has the highest S character, which is the closest to the nucleus, which makes that negative charge the most stable. Okay. Any questions on that? Okay, let me give you guys practice problems on this acidity stuff here for each acronym. Okay, let's do 1, 2, 3, 4, 5. Five of them. Well, actually, let's do seven because one of them has a lot of different factors to it. Okay, so for each of these seven practice problems, circle the one that is the more acidic molecule and also explain why. What's the reasoning that you circled that more acidic molecule? Right. I'll give you guys like 3 to 5 minutes for this. And then after this, we'll go over hybridization, specifically when some parts are seen as sp3, but some can be seen as sp2 due to resonance, as requested on the Discord server after this acid base concept. Okay, let's look at the first one here. Did you guys choose the left or the right one as the more acidic structure, and why? Oh, right. So as it is right now, water neutral is more stable than this hydronium H3O plus ion, right? But the question that I'm asking you here is which one is more acidic? Meaning that when it gets deprotonated, right? What conjugate base will be more stable? So this is the acidic form. We want to draw out the conjugate base after it gets deprotonated. So for example, when some kind of base deprotonates this water, we get this hydroxide ion. And when some kind of base deprotonates this hydronium ion, we get this H2O water molecule here. These are the conjugate bases of these acids here. And then from these conjugate bases, we then determine which is more stable, right? Another way you can think about it is pKa, right? But I like to think about it as the conjugate base route better because some professors don't allow note cards. Does Ling allow a note card for his exams, midterms? Yes. Okay. Um, so you could include the pKa's in the note cards as well, and then like look at the note card to see which structure is more acidic. But I don't recommend that. I actually recommend understanding the reasoning behind it. So in future classes in 118B, 118C, there will be acid-base questions like this. It's best to understand why something is more acidic than the other, right? And like Safarna said, the left one is more acidic because the pKa is 0, which is going to be less than the pKa of the water. But the actual reason why the pKa is lower here is because when we draw the conjugate base, this water molecule here, the conjugate base that I drew in blue, is more stable than the conjugate base of water because neutral charge is more stable than the negative charge, right? Let's do the same for these acids here. If we deprotonate this H2S, we will get HS minus. If we deprotonate water, we will get HO minus. Which negative charge is more stable? The negative charge on the sulfur or the negative charge on the oxygen? And why? All right, so that's the other factor that we could talk about as well, electronegativity. But in the periodic table, oxygen and sulfur are on the same column, so they have similar stability. Oxygen is more electronegative than sulfur, so that's one of the reasonings why, right? But the bigger factor is going to be atom size. So atom size here, especially in the same column, will take priority, making this the more stable conjugate base, right? The negative charge on the sulfur is more stable than the negative charge on the oxygen because this is a larger atom, right? The atom size is taking priority here. This is atom size. This is talking about charge. Okay, now let's draw the conjugate bases of these molecules here. When we deprotonate this acid, we get this conjugate base. When we deprotonate this acid, we get this conjugate base here. Which negative charge is more stable and why? Oh, sure, I just realized that the correct answer has a similar pattern here. Right? Think about this negative charge and this negative charge here. They're on the same atom, oxygen, right? So that doesn't matter. The atom size doesn't matter. Same atom size. They have the same charge, the conjugate bases. They're both negatively charged, so the charge doesn't matter, right? But what can this negative charge do that this negative charge cannot do? Think about the surroundings. Resonance, right? We see that this negative charge here can do resonance with this carbonyl. A carbonyl is a carbon double bond oxygen. I would be familiar with this term, carbonyl, carbon double bond oxygen, right? And because it can do resonance, it's more delocalized. The negative charge can shift around the molecule more, making it more stable. More stable conjugate base comes from the more acidic acid. Okay. Okay. I'm just gonna deprotonate all of these acids and draw the conjugate bases like this. Okay. So these are the conjugate bases now. That's the first step when you're determining which one's the stronger acid. Always draw the conjugate base and then determine the stability of the conjugate base. Let's look at 4. Which one is more stable? Which negative charge is more stable? Okay. They have the same atom size, the same resonance, the same charge, negative. So the next factor is induction, right? Right. It's gonna be the right one because fluorine is more electronegative than chlorine, making that able to withdraw electrons from that negative charge more powerfully, making it more delocalized, more stable. Whereas chlorine, since it's less electronegative, it doesn't have as much as a strong pull than chlorine does, making this negative charge not as delocalized, not as stabilized. That's right. Now, for the 5th one, which one would it be? Right as well? Yep. Because there's more of it, more of the fluorine. The 6th one? Right. So this is a tricky one right here. Even though fluorine is more electronegative than chlorine, right? This fluorine here is so far away to this negative charge that the electronegativity factor decreases. Chlorine here is closer to this negative charge, making this chlorine able to stabilize that negative charge better, right? So that's the 3rd factor that we talked about for induction right here, which is the proximity to the negative charge. The first 2 reactions I gave you guys was like the more electronegative atom versus the larger number of electronegative atoms. The 3rd example here, which is the tricky one, is the proximity to the negative charge, right? So this first one here was talking about like more electronegative atom. This second one here is talking about larger number of electronegative atom. And this one here is talking about proximity to the negative charge. Closer, stronger pull. Farther, the pull weakens, even though this fluorine is more electronegative. Right. Now, for the 7th one, which one is more acidic? So first, let's draw out the conjugate base when it gets deprotonated. Negative charge there, negative charge here. Which negative charge is more stable and why? Right. Oh, right. So what is the hybridization of this carbon here with the negative charge? Is it sp2 or sp3? This carbon here holding the negative charge. Yep, sp3. That's correct. Because it has 4 bonding groups attached to it. 1 single bond, 2 single bonds, a pair of electrons, and a 3rd single bond right there. So that's 4 bonding groups, making that sp3. What about this carbon here? That is on the triple bond. What is the hybridization of that? sp, right? Which one has higher s character, sp or sp3? sp has higher s character, so it would be the left one. The left one is more acidic because this one has higher s character, right? The reasoning is correct, higher s character, but the left one here has higher character, the s character, than the right one, right? So this factor here is talking about orbital or hybridization. Okay. Any questions on this concept so far? This were just like my simple examples on it. I'm gonna give you guys Levin's practice questions related to this, and then we'll move on to resonance and hybridization. But I just wanted to give you guys some background knowledge on this before I give you Levin's thoughts. Okay, let's move on. Okay. So these lines here, Levin's wanting you to explain why you circled the structure as more acidic, right? So it's very similar to what I gave you guys earlier. That, and we have this H. H. Okay, let's try these one. Okay. For the first one, what did you guys choose and what factor did you use for that? Yep. The one with the SH is going to be more, is going to give a more stable conjugate base because of atom size. This negative charge here can float around more on a more polarizable atom, larger atom. Or more polarizable. Right, same thing. Okay. For the second one, let's just draw out the conjugate bases of this right away. Which conjugate base will be more stable and why? This negative charge or this negative charge? Right. So the reasoning is wait, is my screen mirrored? Like is this left for you guys? Or is this right for you guys? Is my screen mirrored? Oh, okay, okay. I was just making sure. I was like, that's the correct reasoning because of electronegativity, but I thought like I don't know, the zoom camera might have made this seem as the left side. Right. Yeah, it's gonna be this one because of induction. Right. Now let's draw the conjugate base of this and the conjugate base of this here. Which negative charge is more stable and why? Right. The more stable conjugate base will come from the more acidic molecule. Right. So it would be the left one because this carbon here is sp, and then this carbon here is sp2, SP has 50% S character, whereas SP2 has 33% S character, right? 50% S because one S out of the two overall orbitals, one half is 50%. SP2 is 33% S because there's one S out of three total orbitals, 33% S. So the reason why this is more acidic is because it has more S character. Yep. Okay. Are you guys ready to move on to hybridization? And like whenever like there's a resonance, you can do SP2. Okay, let's move on to hybridization. Okay. I'm gonna give you guys a whole bunch of different molecules, and then I want you guys to determine the hybridization of the indicated atoms that I point out for you guys. Okay, we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 practice ones here for hybridization. Let's for resonance. Can you also go over how to draw resonance hybrids, the dashed line thing, and partial charges? Yeah, let's go over that after we go over this hybridization thing. Right. First, what is the hybridization of this carbon here that I indicated? SP2. That's right. SP2. And that's because it has 3 bonding groups, 2 single bonds and 1 double bond. What about this carbon here that is triple bonded? SP. That's right, because it has 2 bonding groups, 1 triple bond and 1 single bond. What about this halogen here? Right. So I don't know what like Ling says like this halogen is, but even though it looks like 4 bonding groups, 3 pairs of electrons, and 1 single bond, Levens, she always says halogens are p hybridized, p unhybridized, p unhybrid orbital. What does Ling say for his class halogen is? Is it usually sp3 or is it unhybridized p? Unhybridized p. Okay, yeah. So here are the weird ones that I want you guys to know, right? Halogens X, they are going to be unhybridized P, and then hydrogens are going to be unhybridized S. Oh my god, this marker is so bad. Let me use this one. Right, halogens like chlorine, bromine, iodine is going to be unhybridized P. Hydrogen is going to be like unhybridized S. Right, and because this is a halogen, this is going to be P right there. Right. What is going to be this hydrogen over here? Yep, unhybridized S. Okay. What about this carbonyl oxygen? What is the hybridization of this carbonyl oxygen here? Yep, sp2, because it has 3 bonding groups, 2 pairs of electrons, and 1 double bond, making that sp2. That's right. Now, how about this oxygen of the alcohol right here? sp3. That's right, because it has 4 bonding groups, 2 pairs of electrons, and 2 single bonds, making that sp3 hybridized. Okay, what about this nitrogen of the amine here? Yeah, it's going to be sp3 because it has 4 bonding groups, 1 pair of electrons, and 3 single bonds. 1 to the carbon and 2 more to the 2 hydrogens that it's bonded to. That's sp3. What about this nitrogen right here? Yeah. So it looks okay. So this is the trickiest thing. Let me yeah. It's gonna be sp2, right? And let me show you why. It's sp2, not sp3. I'm gonna erase everything else because this is the one that he's most likely gonna put in the midterm, right? This is the tricky one here. Let me explain this more in detail. Okay. Nice. Okay. So this nitrogen here, it looks like it has. Yeah, you're right. It's going to be sp2 because of resonance. This nitrogen here, it looks like it has 4 bonding groups, 1 pair of electrons, and 3 single bonds, right? But if you see that this pair of electrons here can do resonance by going down and making a double bond between that carbon and nitrogen, and then popping this double bond onto that oxygen right there to give this resonance structure here, where to draw the resonance arrow, it's a double-headed arrow like that. We are going to get this resonance structure here, right? Where before oxygen had 2 pairs of electrons, but now this oxygen has 3 pairs of electrons. It gained another pair of electrons from that double bond right there. That double bond popped up to give that oxygen a pair of electrons, making that negatively charged. Because oxygen is in a 6 column, it wants 6 electrons to itself. But we see here this oxygen has 1, 2, 3, 4, 5, 6, 7 electrons. So that's 6 minus 7. 6 minus 7 is -1 charge. Whereas this nitrogen here, it has a positive charge because it has 1, 2, 3, 4. 4 electrons to itself, but it's on the 5th column, 1 in 5 electrons. 5 minus 4 is +1. And to like verify this is correct, the original structure was neutral, and in all resonance structures, the charge has to stay the same. It has to conserve. This is overall neutral because the positive charge cancels out the negative charge right there, right? Where we see here that this nitrogen looks sp3, whereas this nitrogen here now looks sp2 because it has 3 bonding groups now, 1 double bond and 2 single bonds. When you can do resonance, when an atom can do resonance, it's going to prefer the sp2 hybrid orbital over the sp3 hybrid orbital, right? Because resonance is going to happen between adjacent p orbitals like that, where the p orbitals can overlap. And in order for the p orbitals to overlap, we need to have an sp2 hybrid orbital, right? If this nitrogen was sp3 hybridized, then those will have no p orbitals at all. But if this nitrogen was sp2 hybridized orbital, then that nitrogen would have a p orbital allowing for resonance. And resonance is a good thing. It's a stabilizing factor, which is why when this nitrogen can do resonance, it's going to prefer the sp2 hybrid orbital over the sp3 hybrid orbital, right? Does this make sense so far? Okay, let me give you guys 2 more similar ones here, right? Let's say we have okay. What is the hybridization of this oxygen right here? sp2, that's right. Because it looks sp3 since it has 4 bonding groups, 2 lone pairs and 2 single bonds, but we have to always look out for resonance. If this can do resonance, which it can do with the carbonyl here, then this is going to be sp2 hybridized, not sp3, right? If we have something like this, for example, where the carbonyl was not there, then this is going to be considered sp3, right? 2 pairs of electrons and 2 single bonds. No resonance possible here. What is the hybridization of this carb anion here? sp2 again, right? Because we see that this carbon will have one lone pair of electrons that can do resonance with the alkene like that, giving us this resonance structure here, right? And because this can do resonance, this carbon right here now has 3 bonding groups, 2 single bonds and 1 double bond, right? Did this make sense so far, like how I got this resonance structure from this original molecule? The charges are still conserved because the original molecule had a negative charge, and then the resonance structure that I drew also has a negative charge. So to determine what orbital it is, there is 1 or 2 lone pairs, we have to watch out for resonance. Yes, if there is 1 or 2 lone pairs, you always have to look out for resonance. That's right, that's right. If that pair of electrons cannot do resonance and is stuck there, localized, then it's sp3. But if it can do resonance, like in these examples here, then it's going to be sp2. sp2. That's right, that's right. This is going to be most likely on the exam. I predict that this type of question here is going to be the exam. Right, so be careful of this here. How do you know which structure is preferable again? Is there a resonance structure? Well, when I said like this sp2 hybridized is preferred, I don't mean that this is the major resonance structure. This is the major resonance structure, and this is the minor resonance structure. And why is this the case? Why is this major and this is minor here? Yeah, this major resonance structure here has no full charge, whereas this minor resonance structure has a negative full charge and a positive full charge, right? Charges will make things more unstable, making this minor. What I meant by like this nitrogen preferred to be sp2 over sp3 is because if this nitrogen is sp2, then we would have 1 p orbital on the nitrogen for resonance, right? If we said this nitrogen was sp3, then that means that this nitrogen will have no p orbitals for resonance at all. But we wanted that nitrogen to be sp2 for it to have 1 p orbital that can do resonance with the p orbitals right there. Right. In this example here, they're like pretty major resonance structures because like they have both negative charges. Yeah. Did I answer your question, or what was that not the question? Yeah, no problem. Okay. Are you guys familiar with how to draw resonance structures from? Oh yeah, let's go over that thing that you talked about earlier about the partial charges and the dotted lines with the hybrid stuff. Let's do that. Okay. Okay. Let's look at this right here. Right. Resonance is going to happen between adjacent p orbitals. You can think of those as adjacent sp2 orbitals, right? It could also be sp3 at times, but most likely you're going to see sp2 orbitals, right? Where this carbon is sp2, this oxygen is sp2. What we could do is we could move this bond up onto the oxygen like that to get this kind of resonance structure here. this oxygen gained a pair of electrons, making that negative charge. This carbon, it used to have 4 bonds, but it lost the bond, giving that carbon a positive charge right there. Right? We can do more resonance here because we see that this oxygen here has 2 pairs of electrons, where 1 pair of electrons can go down to make a double bond right there to give this resonance structure here, right? Where this oxygen has a positive charge because it has 1, 2, 3, 4, 5 electrons to itself. But it's on the 6th column. It wants 6 electrons. 6 minus 5 is positive 1. And all of these resonance structures are valid because they conserve the charge. This is a neutral charge. This will be also a neutral charge because the opposite charges cancel out. Where this is going to be the major resonance structure, and these are the minor resonance structures, right? And there are like some factors that determine the major stability of resonance structures. The number 1 rule for that, right, or major stability of resonance structures is the octet rule, right? We gotta make sure that every like single atom in the resonance structure fulfills the octet rule, right? The next thing is going to be neutral charge over charges, right? No formal charges. The next thing is that even if we do have formal charges, we want the negative charge on the more electronegative atom and positive charges on the less electronegative atoms, right? And then this factor here is not as important, but we want opposite charges near each other because they attract each other. So if you have a negative charge and positive charge, they want to be near each other as possible to make it stable. So based on this factor here, which okay, this is important. Which structure is major and minor comparing these 2 minor resonance structures here, right? This is going to be a little bit tricky, like comparing these 2 resonance structures. Which one is major and why? So that was the trick that I wanted to show you guys. The left one here looks more major than this one because the opposite charges are right next to each other. They're near each other, right? Whereas these opposite charges are far away from each other, which is this factor here. But let's look at the octet rule, the most important factor. This is a tricky one. This carbon here does not fulfill the octet rule. It just has 6 electrons, 3 bonds, right? Whereas every single atom here fulfills the octet rule. This carbon, oxygen, oxygen, carbon, carbon has the octet rule. Hydrogens, we don't talk about hydrogen. That's, yeah, right. This right here has no octet. This carbon here has octet. So the octet rule takes priority over that. Okay. So the right one here will actually be more major than this left one, right? In an example where both molecules fulfill the octet rule, then you would go for the charges near each other like that, right? But in this case, this one has the octet rule, this one does not have the octet rule. Yeah. So I would look out for that as well for this resonance factor list. Right. Okay. Now let's talk about some other things about resonance. So this is an important concept here. Negative charges move to positive charges, filling in the void. Right. So I'm going to give you guys two structures, and I want you guys to draw in the possible resonance structures here and the arrows. Right. Okay. So for this first structure here, what would the resonance arrows look like for this structure here? Like, where do I start my arrow, and where does it end up at? Yeah. Yeah. The negative charge will go towards the double bond, because this negative charge here has a pair of electrons, and we said earlier that negative charges will move towards things. So that pair of electrons here will make a double bond right here. This double bond right here that represents two electrons is going to go make a pair of electrons on that carbon to give this resonance structure here. Right? Where this pair of electrons on this structure came from that double bond right there. That bond with two electrons made that pair of electrons right there. This double bond right here came from that pair of electrons that moved right there. Right? It's not going to be this right here. Right? So don't do this arrow. Yeah, don't do that arrow. Yeah, don't do this purple arrow here. What about for this second structure here? What would the resonance arrows look like for this one? Yeah, that's right. The double bond will go towards the positive charge, making a double bond right there to get this resonance structure, right? Where this carbon, it used to have three bonds, but we now gave it a fourth bond. It's neutral. But this carbon right here in the middle lost the bond. And if it lost the bond, it will have the positive charge, which is good because it conserves the overall charge of the structure, right? But there is something else that we could do here, which is this double bond here. It could do the exact same thing like that, right? Giving us this resonance structure here, right? Where this carbon, it gained a bond to make it neutral, but this carbon at the end, the left end, lost the bond, making that a positive charge. Okay, so now let's do the resonance hybrid for this structure and this structure here, right? With the partial charges. So I'm gonna draw out that structure right there, where you notice how the double bonds are delocalized between these three atoms here. That's why we draw dotted lines between these three atoms here. We see that these electrons are not moving to that carbon at all, which is why there's no dotted line at this end here. We also see a negative charge at this carbon and this carbon right here, which is why there's going to be a partial negative charge on that carbon and that carbon right there, right? For this bottom one right here, we see that the electrons are flowing in between these 1, 2, 3, 4, 5 carbons, right? Because we see resonance, like there was a positive charge at this end, it moved to here, moved to there. The electrons are like moving in between these 5 atoms, but nothing touched this carbon here. which is why there's no dotted line at that portion right there. And we see positive charges at this carbon, which is that carbon. We see positive charges at that carbon, which is that carbon, and positive charge at that carbon, which is that carbon right there. So that's the partial charges of the structure with the dotted line like that. So does only one thing move at a time in resin structures in more than two resin structures? When you are drawing out resin structures, one thing moves at a time for the test, right? But in reality, all of these happens at the same time. Like they're constantly flowing like this. This is the resonance hybrid. This is the more accurate picture of what happens in reality. They're all flowing throughout the molecule like this. This is just representing of what happens at a snapshot, one at a time. They give it as like taking a picture of something, and it like that's like frozen in there. But it doesn't do it one at a time. There's actually electrons all throughout this portion of the molecule here, right? Resonance just allows us to see what's going on more clearly, right? Which is most likely going to be tested on the midterm. Draw out the resonance arrows, and he could also ask you to draw out the resonance hybrid right here, where you draw out the dotted lines on where the resonances are flowing, and then the partial charges of where the charges are ending up at here. Yeah. Okay, let's do a similar one that's a little bit more complicated than this here. Okay, someone describe to me what the resonance arrows would look like for this and what the resonance structures would look like for this, and also draw the resonance hybrid with the dotted lines and the partial charges, where the partial charges will be at. And also determine which one is the major resonance structure and why. Right. Okay, let's do one thing at a time. What would the resonance structure, resonance arrows look like for this here? For the previous question, would they all be likely? Would we have a major minus still? Okay, so for the previous question here, uh, uh, so for this first resonance structure right here, we have a negative charge and a negative charge. And they are both allylic, meaning that they are one carbon away from the double bond. That's a position term, which you're going to learn in 118B. This can do resonance with the double bond, which these are the resonance structures like that, right? We said earlier that R groups are electron donating. So at this resonance structure here, we see that R group is donating electrons onto that negative charge. And then we have two R groups here donating electrons onto this negative charge here. Negative charges repel each other, like charges repel each other. So based on that fact, which one looks more stable? The negative charge that has less groups donating electrons to it, or the negative charge that has more groups donating electrons to it? Which one looks more stable here? Does the negative charge on oxygen mean that there is only one set of lone pairs. So no, there is actually more than one set of lone pairs because oxygen here, right, is on the sixth column, so it wants 6 electrons to itself, right? But we see that it has a charge of -1. So X would represent how many electrons that oxygen has to itself. When we solve for X, we're going to see that X equals 7, right? Meaning that oxygen will have 7 electrons to itself. Whenever you see a bond like that, think of that bond as 1 electron to the oxygen, 1 electron to the carbon, because it's shared. There's 2 electrons. 1 electron is shared to the oxygen, 1 electron is shared to the carbon. So right now, it has 1 electron as drawn, but we want 7 electrons on that oxygen. So we have to draw out 6 other electrons. 1, 2, 3, 4, 5, 6. So now this oxygen has 7 electrons to itself. 1, 2, 3, 4, 5, 6, 7. Where as drawn here, there's 3 pairs of electrons on oxygen. 3 pairs of electrons like that. Right. Where this is going to be our major resonance structure because the negative charge here has less R groups donating electrons to it, less electron repulsion. Whereas this is minor because there's more electron repulsion here, more electron groups clashing, right? And this is going to be the minor one because when we talked about carbocation stability earlier, this is primary, right? This has the less hyperconjugation. It's less substituted, less friends, more lonely, less happy, less stable, right? Whereas this one here is secondary allylic. This is also secondary allylic. Since they're both equally substituted, then these two are equally major here, right? But he hasn't gone over like the carbocation stability, carbanion stability yet. He will go over that later on. So I wouldn't worry about that in this this here, right? The factors that I would worry about are like the octet rule for sure. That's the most important one. The no formal charges, that's the second one. And then if there are formal charges, we want the negative charge on the electronegative atom. We want the positive charge on the less electronegative atom. And then the fourth one, opposite charges near each other. But always remember that the top priority, the octet rule. Like everything has to have the octet rule. That's the thing that overpowers every other rule. Right. Okay, so what did you guys say the resonance arrows would look like for this structure here? Yeah, Joseph.
You can move one of the lone pairs down from the oxygen to make a ketone, and then move that carbonyl carbon, or yeah, the alkene, that one, into a carbanion.
That's right.
And
That's
then
one.
that's one resonance.
That's right. Which would look like this.
And then you can move that ketone again into where the double bond of the previous one used to be, and then move that carbanion to make it as a double bond.
Oh, like
And
move
then
it, make a double one here and then pop this double one onto oxygen like that.
no, the other way.
Oh, this way right here.
Yeah.
Right. So we will do that, right? But what happens here? This carbon will break the octet rule because this carbon has 4 bonds.
Yeah, and then you move that one as a carbanion.
Yeah, this one will move as a carbanion. That's the last carbon, the last resonance structure right there. Right. That's correct. Nice. So these are the 3 resonance structures here. Right? Where if we draw out the resonance hybrid, it is going to look something like this. Let me make this more neat really quick. Looks really weird. Right? Where we see that the electrons are flowing between the oxygen atom all the way down to this portion of the molecule here. This portion of the molecule has no dotted lines because we see no electrons moving at this portion of all the resin structures at all. Nothing moving, nothing flowing here, no electron flow here. So that's the resonance hybrid with the dotted lines. But now let's fill in the partial charges. Negative charge on that oxygen will give this oxygen a partial negative charge. Negative charge on that carbon will give this carbon a negative charge. Negative charge on this carbon will give this carbon a negative charge. So that's the resonance hybrid with the partial charges there. How do you know when to stop for the ring structure? Yeah, so for this ring structure here, we had to stop here because we could not make a double bond right here anymore because this carbon here is sp3 hybridized. And we said that resonance will happen in a network of adjacent sp2 or sp3 atoms, right? We see that this is sp2, 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 sp2. This right here is an sp3 roadblock. It blocks resonance. So whenever you see an sp3 atom, that is where you stop. You cannot do resonance there anymore because when we try to make a double bond right there, there's nothing to kick out. There's nothing to pop out to conserve the octet rule. There's no double bond to move. There's no carbocation to fill in the void, right? Because if we try to make a double bond right there, this carbon right here has nothing to move out. This carbon will break the octet rule. It will have 1, 2, 3, 4, 5 bonds. That's not good, so we cannot do that arrow. That's where we stop, where that's the sp3 roadblock there. Did that make sense? Yeah, that's good. Let's do one similar problem to this, and then maybe do some nomenclature if you guys want to do that, or I don't know, whatever you guys want to do afterwards. Yeah. Okay. And we'll end it from there. And then this will be recorded and uploaded to the school community and also the Discord. I will post it to the Discord too, for real. And I will also have office hours, 9 to 10 p.m. Monday, Tuesday, Wednesday, Thursday here. But tomorrow night, Monday, I'm giving a review session for Chem 118C, the summer session. So the office hours will start on Tuesday, 9 to 10. Okay, given the structure here, let's draw out all the resonance structures and its resonance hybrid with the partial charges. Oh wait, I didn't do the last one. I didn't tell you guys to determine which was the major one. Right, we have that. We have this. And we have this. Right? Which one is the major resonance structure and why? That's another potential question that he might ask you in the midterm. And think about the 4 factors: octet rule, no formal charges. If there are formal charges on the negative charge on the more electronegative atom, and then opposite charges will be near each other. But the octet rule will overpower every single factor below that. the first one because the charge is on the more electronegative atom. That's right. This one would be the major resin structure because all of these resin structures has a negative charge. So we have to choose the resin structure that the negative charge is on the most electronegative atom, which is oxygen. And every single resin structure has the octet rule, so we don't have to worry about that octet rule thing, right? Every single thing has octet rule, so we move on to the next factor, which is the electronegativity factor. Okay, let's look at this one here. What would the arrows look like for this resin structure? Here. How would we draw the resin structures? And make sure to do it one at a time, because if you go all the way throughout, then you're restricted to only 2 resin structures. So let's do it one at a time. Right. And what Liebens does is yeah, what Liebens does is that she makes boxes for you to know how many resin structures you will have. But for this new professor that I'm not too familiar with, I don't know if he will provide boxes or if he would tell you to draw this amount of resin structures. Right. Yeah. Let's figure out what's the resonance arrows to get to this middle resin structure and then this last resin structure here, and then determine which is the major resin structure, and then draw the resonance hybrid.
Excuse me, I could try solving the question or solving the problem, but I'm
Yeah,
not sure
yeah.
if my answer.
Yeah, that's fine.
Okay.
If you get it wrong, don't worry, because that's how you learn. Like, that's how you avoid it in the midterm. Yeah, so don't worry
Okay.
if you get it wrong.
Okay, so I think you'd first move one of the double bonds from the oxygen. Is that correct? To the left.
Oh, like to this oxygen right here.
Oh, oh no, so wait. Like to the to the to the chain of the carb to the chain.
Oh, to the chain, to
Oh,
the chain.
yeah. Wait, that's wrong.
Like this right here.
Yeah.
Uh-huh. Right. And then is that the only arrow,
No,
or
and
is
then you would move the double bond to the other or
to this
to the
side right here
yeah,
to make a
or
double bond or to make a negative charge on that carbon?
a negative charge on the carbon.
Yeah, yeah. That's the one that's going to happen. To
Okay.
make it negative charge on this carbon here. So that is one possible resonance structure, right?
Okay.
Which would give you this resonance structure right here, right? The charges do like conserve because at this original structure, we have a negative charge, but the resonance structure that we drew out here, the overall charge is still a negative charge because this positive charge would cancel out with that negative charge, giving that one negative charge right there. But this structure is very unstable because there is a whole bunch of 4 more charges. There's 2 negative charges and 1 positive charge. If you see a whole bunch of charges, think of that as a like a bad sign, right? Like a bad sign of resonance structure. This is very possible, but this is very unstable. Unstable. Very minor. Right? So that's why she did not include it into those boxes. But this is a possible resonance structure. That's like technically a resonance structure, but it's very unstable.
Okay.
Uh-huh. So another tip for this resonance thing, right, is that if you see a negative charge, start with that negative charge and move that negative charge instead of the double bonds.
Okay. So would you first move the negative charge
Yeah,
to the chain
to make a
or to
double
the
bond
ring?
there,
Yeah.
right?
Okay. And then would you move that double bond um out to create a lone pair, or would you?
Right. You can move the double bond out to make a lone pair there, or you can move the double bond to make a double bond here. But then there's something else that has to happen when you do that. What will happen if you move the double bond here? What else would
You
happen?
move the double bond of the oxygen to create
To
a
the
lone pair.
oxygen, right? And
Yeah.
that's why I said do this one at a time, because if you did that route, then you would end here. There's like no other resonance structure you could do, right? So let's do it one at a time by making a lone pair of electrons there, right? That is possible though, like where you can make a double bond here and then pop that up there, right? That is possible. Okay. So that's why Levens does this in boxes. So she makes sure you do it in one step at a time. Because if she did not give you boxes, you could just go through that and like there's going to be a whole lot of regrade requests if she didn't put these boxes to restrict you. She makes it very clear on how many resonance structures she wants you to draw. But for Ling, I'm not too sure on how he does it, right? But I would stick with this route, like one at a time, to get max points as possible. Right. Okay. Once we have this, what's next?
And then you'd move the double bond from the oxygen to create a lone pair.
Double bond to the oxygen to make a lone pair, right?
Yeah.
But think of it like this: what pops that double bond onto the oxygen? What forces that double bond to go into the oxygen?
Oh, creating a double bond, but from the
Yeah,
negative. Yeah.
that's right. Creating a double bond here. So whenever you see a negative charge, always start with that negative charge. Don't think about the double bonds moving first. Whenever there's a negative charge, always start there and then shift the double bonds wherever you want, like this. When we pop that down there, that pops this double bond onto the oxygen right there. Right? That's the thinking behind that.
Okay.
Okay. And then we have that. And then the oxygen here will have a negative charge. These are all the resonance structures, the major ones. This is also a resonance structure here, but very, very minor. Which one of these is the most major resonance structure, the most stable one?
Would it be the last one?
Yeah, the last one, because the negative charge is on the electronegative atom, the most electronegative atom, and all of them have the octet row, so we don't have to worry about that. Right. Now, let's draw the resonance hybrid of this. Where would the electrons flow for this resonance hybrid?
It would be between the first negative charge on from right there, and then go reaching up to the oxygen.
Yeah, all the way to the oxygen right here. That's right. No electrons here at that methyl group because there's nothing that moved there. No electrons at this bottom portion of the thing because nothing moved there as well. Those are the dots. Now, where would the partial charges be, and what kind of charge is it going to be?
It'd be a partial negative charge to the left, right there, yeah, and then another one where we had the lone pair, and then on the oxygen.
Yeah. So that's the resonance hybrid for these resonance structures here, and that's it for resonance. Okay, that's good. Nice. Any last minute questions before we end?
Hi, I have a quick question.
Yeah.
I forgot where I saw this, but I remember like in some questions they put a bracket and then they put a negative sign like on the right top. I forgot what does that mean?
Oh, right. So technically, when we draw resonance structures, we have to put brackets in them as well to represent that these are resonance structures, right? So there has to be a bracket here and a bracket here, right? Another way to show this right here is this right here. So if we have these structures shown like this. Right here, where they do give you the pairs of electrons, but they don't show the full negative charge right there. You can just put the negative charge for this whole bracket to show that there is a charge of -1 for all of these resonance structures here. Right, where they don't put the negative charges in the individual resonance structures itself. They just say that all of these resonance structures has a formal charge of -1 like that. Right, this is the exact same thing as this right here, where there's a negative charge here, negative charge there, negative charge there. But they do have to include the pairs of electrons to show like what atom will have the negative charge. Did that make sense? Yeah. Yeah, no problem. Okay. I will edit this video, put timestamps on it so you guys can skip to the part that helps you the most and post it to the Discord and the school community. And maybe see you guys in office hours this week. And good luck on the midterm. Wait, I think this Wednesday, July 10th. Yeah. Yeah, good luck on the midterm. Yeah. No problem. Me too.